Okay, so kind of looking ahead here to where we're at and where we need to be, looks like we're pretty much on track. I wish I had like one more day, but I think I always wish that. So we're going to spend a little bit of time working on these particular problems from your digital workbook. We started on them on Friday, okay? We're going to work on those, and if we finish those up, we'll start the assignment for simple harmonic motion today, and you'll have some time on Wednesday to work on it as well. Tuesday, we're going to do our lab on pendulums, okay, so tomorrow will be a lab, but it's a pretty straightforward, easy lab, so you should be able to get much of it done in class, and you should be able to get much of the assignment done in class as well, because you're going to get probably some time today and some time on Wednesday to work on that, and then that will end the first half of the unit, and then we'll move on to waves. Okay? My hope is that we will get through to interference before Christmas, and then all I will have left to do after Christmas in the like 6 days we would have would be standing waves and Doppler effect, okay, which I should be able to easily do in 6 days and have time for a unit exam and maybe a day of review, maybe 2 if we're lucky for the fun. Okay, but just kind of looking over the calendar and what we have left to cover, that looks like that's a possibility. Okay, I would not expect to get more than 2 days of final exam review for this class. That would be a best case scenario. Okay, a worst case scenario is I have to rush and we don't get any final exam days to review. Okay, that is also still a possibility. Right, so just know that just because of the way the calendar fell, we got shorted about 4 days. Okay, so we're a little bit behind where I'd like to be, but I think we'll be all right. Okay. So what I would like you guys to do is work on those questions there. Okay, I'm going to give you a bit of time on those, and then we will go through them if there are any questions, and then we'll kind of see where we're at. Okay. Okay, so got object vibrating end of a horizontal spring, so we know what K is, 18 newtons per meter. Maximum speed, which occurs at equilibrium, is 0.35 meters per second. We know the amplitude is 0.29 meters. We're looking for the speed of the object when its displacement is 0.1 meters. All right, there's one really important piece of information that I'm missing. Right, so I'm going to say I'm looking for VF, and I know XF is 0.1 meters. But if I'm going to find V, what's part of the kinetic energy formula that I don't have in this question? Mass. But I can find it by doing 2 conservation of energy problems. Okay? I'm going to do one that involves equilibrium and maximum amplitude, because the energies at those 2 places are the same. Okay, I know the maximum speed, I know the maximum amplitude, and I know K, so I can isolate M, which I need to do the second part of this. Right, so M is going to be Ka squared over V max squared, because the halves will cancel. Okay, so it's actually a 2-step problem. So 18 times 0.29 squared divided by 0.35 squared. All right, so we're looking at a mass of 12.3 kilograms, 12.35 kilograms. And now I can set up the second law of conservation of energy problem, okay, where I'm going to say E initial equals E final, and that's going to be 1/2 Ka squared equals 1/2 Kxf squared plus 1/2 MVF squared. Okay, now that I know M, the only thing in that formula I don't know is VF. So I'm going to subtract the Kxf over here, so I'll have 1/2 Ka squared minus 1/2 Kxf squared equals 1/2 MVF squared. I'm going to get rid of the halves because it's in every term. Okay, and then I'm going to divide both sides by m, now that I have it, and then I'm going to square root. Okay, so when I'm plugging in my numbers, that's going to be 18 times 0.29 squared minus 18 times 0.1 squared divided by that 12.35 kilograms. Okay, and when I do that, I should get the 0.33 meters per second.
So when you're doing your energy initial and energy final, the second part, the KXF squared and then the NVF squared, like, so what are those? The KXF is the...
This is the potential energy final, and this is the kinetic energy.
Oh, okay. Oh, that's...
Yeah?
I remember that, yes.
Any other ones? That's about as tricky as they get for conservation of energy in simple harmonic motion. Okay, how are we feeling about that stuff? Like, we're okay with that? Like, we're ready to be done with that? I didn't get as many, like, vigorous up and down nods there. Okay. How many people are, like, done up to, let's say, up to 14? I'm going to hand out the assignments. Okay, and you guys can get started on those. They start out pretty straightforward. They're like, you know, period of a mass on a spring, period of a pendulum. So they start out with those kind of questions. Then they move to a few Hooke's Law questions, and then a few of these. That's really all we've gone over in this unit thus far, is period of a pendulum, period of a mass on a spring, Hooke's Law, and energy. That's it. Okay. So I'm going to hand those out, and I'll go over the instructions for it. Okay, and then you'll have the remainder of today's class and probably the majority of Wednesday's class to work on that. Okay, and we'll have our pendulum lab tomorrow. Okay, so you've just got your assignment here for, like, well, I said first half. It's really like the first third of the unit. Okay, simple harmonic motion is actually like the first third of it. So don't overthink them. Okay, remember things like significant digits, okay, and units and important things like that. Okay, so for question number 1, it's just a simple pendulum question. Okay, you know the period there, you're looking for its length, and obviously you're assuming that it is located on Earth where g is 9.81 meters per second squared. You always assume that unless you're told otherwise. Okay, for question number 2, you are told otherwise, that this pendulum, this grandfather clock, is being moved from one location to another. And it has to be recalibrated because gravity is different, and that affects its ability to keep accurate time. All right? So you know that it's 1 meter long, and it keeps accurate time where g is 9.83. So you would have to calculate how much shorter or longer to make the pendulum at the new location where g is 9.78 meters per second squared. So in order to keep accurate time, it needs to have the same something at both locations. Okay, you gotta figure that out and go from there. All right, number 3, another pendulum question, distant planet. So you're being, again, told otherwise. G is not 9.81 here, and you are being asked to calculate it, okay, from their data. Now, something important on this one. The pendulum executes simple harmonic motion and makes 100 complete cycles in 280 seconds. Okay? 100 cycles. Measured or counted? Counted. That's something that comes up all the time in this unit. Counted numbers versus measured numbers. Something like period is measured. Okay? Something like wavelength is measured. But the number of waves or the number of oscillations is not something you measure, it's something you count. Okay? Do counted numbers affect your significant digits? Keep it in mind, it comes up several times on this assignment. Okay? The number of oscillations or swings are counted numbers. Okay? All right, so number 4, you got a wrecking ball. And once again, we got something about the number of complete cycles. Okay, measured or counted, you decide. Okay, so on this one here, you've got two different pendulums, a wrecking ball and a little rock on a string. Okay, and all they tell you is that the little rock goes back and forth 5 times in the amount of time it takes the wrecking ball to make one complete cycle. So you probably have to calculate something from the first to use for the second. Right? So probably a 2-part problem for that one. Okay, for number 5, another pendulum question, and there's a little bit of explaining to do in part C. Okay, just a little mathematical explaining, but you do have to do a little bit of explaining there. Okay, so you're looking for period for part A, and you're looking for how long the pendulum would have to be to double the period, and then explaining why it's not just double the length. Spoiler alert, it's not just double the length. Okay, number 6, another pendulum question, but this one is on Earth. Sorry, it's not on Earth, it's on the moon, where gravity is 1/6 that of Earth. Okay. All right, number 7. This one is the hardest question on the assignment. So I'm going to give you a little tip here. In question number 7, you are not actually going to find mass 1 and mass 2. You don't have enough information to calculate the masses. The question never asks for them. It asks for the ratio between the masses. So I would say you are probably going to calculate numbers that represent those masses, because you know there's one thing the 2 situations in this question have in common, and that is the spring being used. In the first part of this question, the spring has only mass 1 on it. In the second part of the question, the spring has mass 1 and mass 2 on it. Okay? Think about that, because you're going to be calculating the ratio between the masses, but you have to remember that in the second question, both masses are on the spring. Okay? So if you're trying to find the ratio, you have to think about that. Okay? All right. Since it's the same spring, you're also not given the spring constant. Is that a problem? It's only a problem if you actually want to calculate the real masses. Did I say you had to? Okay. Could you just pick a number for K? Okay. All right. For number 8, you have a spring constant, 1,526 newtons per meter. You have the frequency. Okay. What mass is suspended from it? What comes up a number of times on this assignment is that formula as well, T equals 1 over F. Okay, think about that. Number 9, okay, you have a spring and it's mounted on the floor and oriented vertically. A block is placed on top of the spring, it's pushed down, starts to oscillate. You're just looking for the frequency. Don't overthink that one. Okay, that one's pretty straightforward. Bungee jumper question. It's another mass on a spring question. Number of oscillations, okay, measured or counted. Don't overthink that one either. Okay. You know what? The point values are different on yours on this, aren't they? I forgot to update the point values. Yeah. The last 2. This one's actually only out of 5. This one's out of like 3, and this one's out of 3. It's only out of 3. Think about how much work is likely involved. I would say like givens, a formula, and an answer. Okay, would be really all that would be involved there. Don't overthink those 2. Okay, number 11, that one's got a bit more work to do with it.
Did you say 13's out of 3?
Yes.
Okay.
12 and 13 are out of 3, 11's out of 4. I think the point values on this one are all wrong. I think I changed them all. So just keep that in mind. Look at the point values on your sheet as an indicator. I think that was throwing people off. I for some reason had these out of 6, which is ridiculous. There's no way there's 6 marks worth of work for those 2 questions especially. All right. if there's questions, let me know, but you got the remainder of class today, and you'll probably get the bulk of Wednesday, but I don't think you'll need it, I honestly think you'll get done this fairly quickly.